Hello student, today we will learn about deterministic finite automata. A deterministic finite automata or DFA is defined by five tuples. What are those five tuples? Suppose this M represents the DFA, M is the machine. Five tuples which are necessary to define DFA are capital Q. Capital Q is the finite set of internal states. Okay, so the machine will have some internal state that will be finite and that is represented by capital Q. Then we have second tuple, that is sigma. Sigma is a finite set of symbols called the input alphabet. The machine will read certain input some symbols and they are represented by sigma. Third we have this delta, the transition function. It is basically upon uh, reading some input alphabet sigma from a state, the automata moves to another state. This is the transition function. The fourth tuple is q0, that is a member of capital Q, that is basically the initial state. And finally the fifth tuple capital F is the final state. This is a subset of Q. So whenever we have a DFA, it can have more than one final state. So capital F is the set of final state. It can be more than one also. It can be only one, it can be two, three, and others. So now we will see how this finite automata basically operates. How this finite automata operates. Now we will see. We can see uh, this by a figure also. Suppose this is the example. This is the figure. Okay. Here capital Q represents basically three states Q0, Q1 and Q2. The in, input symbols are small a, small b, Q0 which is represented by a arrow in the left side. This is the symbol for initial state. We can also see here initial state is represented in this manner. The vertex having a arrow in the left side and final states will be represented by two circles. Okay, we have already discussed this, that the final state can be more than one. And also note one point, that the computation means the finite automata does not necessarily halt when it reaches the final state. Understand it in this way, that suppose we have been given a particular set of string. String is formed from the concatenation of different alphabet. So we have a string, and now the question arises whether the finite automata will accept that string or not. So it will start reading the input string one alphabet at a time starting from the left hand side. So in that case, suppose at a certain point the upon reading a certain alphabet it goes to the final state. Then if other alphabet are also there in the string, then the machine will go on reading those alphabet also and it will change its state. And after the completion of the string, suppose the machine, or you can say the finite automata, is at the any one of the final state, then we will say that that alphabet has been accepted by that finite automata. So here we can see the machine suppose starts from Q0. There is only one single final state here, Q2. This is represented by the double circle, and the initial state Q0. The left hand side we have a arrow. Suppose this machine read, suppose the alphabet given is string given is AB. So the machine will start from Q0, it will read A, it will go to Q1, then it will read B, and it will go to Q2, and Q2 is the final state. In this case, the string AB is accepted by this automata. Suppose we have been given a string BA. In this case, from the initial state, the machine will read B and it will remain in its initial state, because Q0 after reading B, it again it does not change its state, it resides in the same state. And the second alphabet is A, so after reading A it will go to Q1, and here the machine will halt. And this is, since it is not a final state, we will say that BA, this string, is not accepted by the DFA, the deterministic finite automata. We can see here the all the five tuples are written here. Capital Q, as I have already said, this is Q0, Q1 and Q2. These three are the different states. This is the finite state. Small a and small b are the two input alphabet we have already seen here, and the transition function, which that is represented by the diagram, it is also written here that Q0, the transition from Q0 upon reading input alphabet A is the new state Q1. This was represented by this method. Capital Q, upon reading certain input alphabet sigma, it will go to some other state, capital Q. The same thing is written here, that the transition function Q0 reading A, it goes to Q1. Similarly, Q0 reading B goes to Q0. Q1 reading A goes to Q1. Q1 reading B goes to Q2. So all the different possibilities uh, from a particular state and all those input alphabet, all those transitions are given. Here Q0 is Q0 itself. So the initial state is already given as Q0, and capital F, this is the final state, and Q2, as we have seen in the figure, there is only one final state. It can be more than one also in some other given automata. So this is the definition, and this is the transition graph. Basically this is the transition graph. So we can say that the DFA is defined by the five tuples, this capital Q, sigma, gamma, Q0 and capital F, and it is represented by the transition graph. Transition graph is like this. And we have also seen that in transition graph, state is represented by simply a circle, and initial state by the left arrow in the circle, and final state by two circles, two concentric circles. And also for final state, you have to note in your mind that it can be more than one, and it also does not mean that the computation halt when it is reached. The computation will halt when we have read all the alphabet of the given string. So this is the DFA. We have seen how the transition, this is the transition function. We have seen this in detail, uh, and also transition graphs. These are basically are used to visualize and represent the finite automata. This is the definition. You can see what is there in transition graph. In transition graph, basically vertices are there, which are representing states, and edges are basically the transition. It will be represented by some input alphabet on top of those edges. The labels on the vertices are the name of the state we have seen, and the labels on the edges are the current values of the input symbol. So we have written all those things which we have already described in the given figure. This is for your understanding. And the vertex associated with q0 is the initial vertex. It is represented by the arrow in the left hand side, and while those labeled with qf belonging to capital F are final vertices. So this is the transition graph, and this was the transition function defined, and it is written all those things which we have already seen in the given figure. We can see uh, when the end of the string is reached, the string is accepted if the automation it is in final state, otherwise the string is rejected. We have already said those things while we were looking at the figure. And how the input basically mechanism go, the input mechanism go move only from left to right and reads exactly one symbol on each step. So we have already seen those things. So this is how the DFA operates. It reads a particular string one by one from the left hand side, and when it halt after reading all the alphabet of the string, if it halts at non-final state, then we will see that the string is accepted by not accepted by the machine, and if it halts at one of the final state, then we will say that the string is accepted. Now we can see one more thing, that is a extended transition function. So what is this extended transition function? We have already seen about a particular alphabet how the transition is defined like this. This is the transition function for a particular uh, alphabet A. Suppose the machine is starting from Q0, after reading A goes to Q1, and from Q1 after reading B is go to Q2. So we can write this extended transition function like this. From Q0 reading AB, it will go to Q2. We have already seen from Q0 reading A Q1, Q1 reading B goes to Q2. So from Q0 we can say after reading AB, always see from the left hand side one by one. From first A it will goes to Q1, after reading B it will go to Q2. So we can write this the extended transition function. It will be written somewhere so you can understand what is the meaning of the extended transition function. This lambda represents the empty string. Okay, this represents the this lambda represents the empty string. Empty string. Okay, so this lambda represents the empty string. This extended transition function is written in one other more way, like this. For all string w and input symbols as suppose wa from the state q, it will be q w this transition, and after this w it will again read a to complete this wa. So this is the extended transition function. When you will write some uh, string, then you can imagine how this extended transition function is working. Now we will move to the language. What is the language? In the very first introductory chapter, we have seen the machine from alphabet, string, then finally the language. So we can also see here the alphabets are defined and the finite automata is accepting certain string. So what is the language? Language is the set of all the string accepted by the automata. Okay, so we can say here what is the definition. The language accepted by a DFA machine M represented by these five tuples is the set of all strings on this sigma, the input alphabet accepted by M. We can see we will write in a formal notation like this. Suppose W is a member of Sigma star we can it is basically the star closure of on sigma. It will be the extended transition function q. This q will be the, this is basically q0. It should be q0 from the initial state. It will go to final state after reading this w. So then this w will be a member of this language. Okay, and there is a relation between the language accepted by the DFA, and that language is called a regular language. So whenever there is a DFA, it will read some set of strings, and the union of those set of strings is the language of that DFA, and the language of DFA is regular. It's called a regular language. So uh, we can read this. Every finite automata accepts some language. We have seen that a certain given DFA, it will read some language. Language means the set of the set of strings strings that will comprise the language. So all DFA will read some strings, and that set of those strings is basically the language. So every finite automata accepts some language, and if we consider all possible finite automata, we get a set of language associated with them, and that family of that language is basically called the regular language. So we can say that a language L is called regular if and only if there exists some deterministic finite automata M such that L is equal to Lm. So all the languages of deterministic finite automata will basically a member of regular language. So a language will be regular if there is a deterministic finite automata for that. If and only if is written there. So you can say in both sides language is regular when there is a deterministic finite automata for it, or if there is a deterministic finite automata and the language generated by that finite automata will also be regular. It is true in both the directions. Okay, so here we complete our discussion on deterministic finite automata. In the next lecture we will see non-deterministic finite automata. Thank you.